and we had to neutralize the solution that we had. We had it, what was it, the hydrochloric acid. We had to add some baking powder to that, the sodium bicarbonate. And the more we added, though, they just kept getting colder and colder by the time we had to get rid of that solution. Right? So when, and it might be a little, sometimes it's a little difficult to understand this endothermic reaction because it's absorbing heat. We figure if it's absorbing heat, then why isn't it getting hotter if it's absorbing the heat, right? So what's meant by it's absorbing heat is that it's using the heat around it. Heat is being put into that reaction. So here, heat if we have to put heat into a reaction, right, this is what we would consider an endothermic reaction. If we have to put it, if it's going to absorb heat, so it uses that heat for that chemical reaction to take place. Right? So it's not getting hotter, it's just using that heat for the chemical reaction. So any heat that's around it, it's absorbing that heat, it's using that heat, but this is why it ends up being colder. So anytime we have to input heat, this is an endothermic reaction. And anytime we're producing heat, it's considered an exothermic reaction. So endothermic, exothermic reactions. Right. These instant ice packs, these get colder here. This is an endothermic reaction. And here we have this acetylene torch, endothermic reaction, because there is a lot of heat being given off there. Now, units of heat. When we say that Q is heat, and this Q here also represents heat. This is just a variable that we use for heat, right? We use M to represent mass, right? So here, right, just like we use T is temperature, right? T is not a unit. T is just a variable we use for temperature. So Q is just a variable we use for heat. Now these are actual units of heat. So you'll recognize these, right? Calories should be recognizable. Okay. So we have calories. We'll put units of heat. So we have cals. 1 calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius. And that is equal to 1 calorie. And then if we have 1,000 calories, right, we have what's called kcals, or kilocalories. You'll actually see both. So these are equal to each other right here. Kcal, kilocalories, they're equal to each other. And these represent 1,000 calories. So this is 1,000 calories, 1,000 calories. And here, I'm going to split this off here. So this is just 1 calorie. These all represent 1,000 calories. Chemists, like, we need shortcuts for everything. I don't know who thought of this one, but apparently the capital K is too much to write. So we do this. Capital C is the same thing as a kilocal, same thing as a kcal, right? This also represents 1,000 calories. So there is a difference between little c, 1 calorie, capital C, 1,000 calories. And these are just some common ones. Now, the SI unit for heat we use is what we call the joule. We've already used joules in calculation before, and it is defined as one moving, excuse me. So the amount of energy used when a force of 1 Newton moves an object 1 meter. And we have this definition here: 1 calorie equals 4.184 joules. So we have 1 calorie is equal to 4.184 joules. You will notice here the amount of energy required to raise 1 gram of water, 1 gram of water by 1 degree Celsius. 1 gram of water by 1 degree Celsius. So we're also going to talk about something we call specific heat. So heat capacity, right? Heat capacity is the quantity of heat that some matter is going to absorb or release, right? So here we have this capital C here, right? It's not a capital Cal, it's just a capital C. So our capital C represents heat capacity. And it says our heat capacity, let me write this down. I think we might need it later, just in case we need it later. So capital C is equal to, what does this represent? Heat, right? So this is heat in terms of cals or kcals over some change in temperature, right? So heat capacity is an extensive property, right? So for example, the heat capacity of some large cast iron pan is greater than the heat capacity of a small cast iron pan. So heat capacity is extensive. It doesn't matter how much of it you have. Right? If I have some matter, it depends on how much I have. That means that it's an extensive property versus intensive. If it's intensive, it doesn't matter how much I have. Right? But here, it is an extensive property. Then we get to the specific heat capacity. Specific heat capacity is an intensive property. Only depends on what the substance is. Right? Only depends on what substance is, and we take in consideration. So it's little c here, right? So this is heat capacity. Versus little c. This is specific heat capacity. So capital C, small c. And we're going to take an example here, this little pan here. Right? So a large pan versus a small pan. So due to the larger size of the small pan, the heat capacity here is greater than this heat capacity here. But the specific heat for this pan is the same as the specific heat for this pan. Right? But the heat capacities are different. So let's actually take a look at that. So here it says the heat capacity of a small cast iron frying pan is found by observing that it takes 18,150 joules of energy to raise the temperature of the pan by 50 degrees. So the heat capacity of the large pan versus the small pan, right? Because it does, so the small one, is that the heat capacity of the small cast iron pan? Is going to be 18,150 joules, and the temperature change on that was 50 degrees Celsius. So what's the heat capacity of the large pan? Just a quick division problem. So heat capacity of the large pan, the small pan. What was it?
Small one. The small one's 363.
And for the large pan. What is it?
1840.
So we can see that is true. So as far as heat capacity goes, is that it is an extensive property, right? Is that the small pan versus the large pan has a larger heat capacity. Well, now let's take a look at specific heat. So the heat capacity right here, let's see, the heat capacity of small pan is found by observing temperature. But this time we have a mass of that small pan. So if we include the mass of that, here's the specific heat of the small one. And it says we're still using 18,150 joules, but our mass this time is, what is it, 808 times 808 grams times 50 degrees Celsius. And the specific heat of the large one, how much did this is 4,040, all right, so 4,040 grams times 50 degrees Celsius. So what is the heat capacity of this iron pan when it's just small, right? 808 grams. .45 joules per gram degrees Celsius. And for the large pan,
.09.
Interesting. Oh, I wrote it wrong. Let me fix this. Hold on. I didn't use the same joules here. 9,700 joules. There we go. Now hopefully they come out to be the same.
Yeah, .45.
Like this?
No, just
0.45. Like this?
Yeah.
So we see the specific heats are the same, right? Specific heat is the same while heat capacity is different. So all these substances have different specific heats, right? Every substance has a different rate at which it'll absorb heat or release heat, right? Different specific heats. Right? Anybody here own a pool or have a pool in their house? Right? During the middle of the summer, water is kind of cool even in the afternoon, but by the time the evening comes, the sun goes down, the water's kind of warm. Right? Even though after the sun went down, simply because it takes longer for water to release heat versus the cement that's back there. Right? When you go to the beach, if you've gone to the beach, right, the temperature of the water is different than the temperature of the wet sand, which is different than the temperature of the dry sand, which is different than the temperature of the black asphalt, right? They've all been under the sun the same amount of time, but each one of them takes a different amount of heat in order to raise its temperature, right? There's a different amount of heat needed to raise its temperature. So here, these are just, you don't have to memorize this table. These are just different examples where we see is that silicon, right, doesn't take much heat to raise up. But we can see that water takes a lot more time to heat than silicon does, right? Silicon will get hotter faster than water will. Right? So that's what these, so the smaller the number, the faster they are, because there's not that much heat required in order to raise that temperature by 1 degree Celsius. So here's our formula for heat. This was also in the lab that we did. So heat is equal to C. What does C represent? Specific heat, right? Specific heat times mass times our change in temperature. So this is, I'm just going to put SH for specific heat. This is going to be our mass, and this is our change in temperature. Very important to note here that when we're talking about change in temperature, temperature final minus temperature initial, it's not bigger number minus the smaller number. Don't be afraid of negative signs when we're talking about specific heat and when we're talking about temperature change. Okay? Looking over the labs that some students did is that they removed the negative sign for some reason. Like, oh no, I didn't want it to be negative. Well, it's okay to have negative, right? Because, right? Is that when we're talking about these, right, is that heat, right, heat absorbed, heat lost is the same value, just in opposite magnitude, right? So when we're doing temperature, it's always finest minus initial, right? The substance will gain energy if the final is greater than initial. Then your Q will be some positive value. If the initial is greater than the final, then our Q is going to be negative. Right? That is some loss of thermal energy. Let me take a quick pause. Why did this not update? Let's close this up. All right, well, maybe it was. Oh no, I think we're good. All right, so just a couple problems here. So we can use this formula as long as we understand what we're looking at as far as these values go. So a flask is containing 8.10 times 10 to the 2 grams, so 800 grams of water. So 800 grams of water, that's going to be our mass. The temperature of water increased from 21 degrees C to 285. So I already know it's going to be some positive value because my final is greater than my initial. Right? So we do final minus initial. And how much heat? So we're trying to answer this question here. How much heat did the water absorb? And it gives us, oh, and then we have this here. So what we haven't talked about is the specific heat of water. So the specific heat of water was in this table here. So Specific heat of water, 4.184 joules per gram degree Celsius. So this is where this value comes over here. Okay. This value is going to be 4.184 joules per gram degree Celsius. And we take all those values and we'll say, okay, the amount of heat released is 2.1 times 10 to the 5 joules. So let's work out another problem using the same formula for specific heat, or for heat. So how much heat in joules must be added to 502 grams of iron skillet to increase its temperature from 25 to 250? The specific heat of iron is 0.449 joules per gram degree Celsius. So how much heat? The specific heat is what? So 0.449 joules per gram degree Celsius. The mass of this iron skillet is 502 grams. And the temperature change from 25 to 250, so my final is 250 degrees Celsius minus 25 degrees Celsius. So just to make this simple, we'll put 0.449 joules per gram degree Celsius times 0.502 grams times 225 degrees Celsius. Okay. So notice here we're not converting these to Kelvin, right? And that's because specific heat is in degrees Celsius, not in Kelvin. So there's no need to convert these to Kelvin. So here, what is our answer? What is the, how much heat in joules have to be added? And let's also work on our units here. So this unit cancels out this unit, and this unit cancels out this unit, so we are just left with something in joules. And it's probably going to be some pretty large number here. What was that? 50.71. Is this what we got, everybody? I haven't calculated this out. Yeah, all right. Yes?
Is it 502 grams or 2,500?
Oh, you're right, Christian. Well, how about we do this? How about we had a, let's see the difference here. So instead of erasing this and backtracking, how much heat would be required using 0.449 joules per gram degrees Celsius. Time was one that's 502 grams times 225 degrees Celsius. So yeah, one that's 0.52 versus one that's 502.
50,714.5.
Right? So because we have more mass, we're going to obviously need more heat in that. Thanks for catching that, Christian. If anybody's ever driven out towards Vegas, not to Vegas, but towards Vegas, you ever see all those, that plant out there? So that's not necessarily a solar plant. Those aren't solar panels. Right? Is that those are mirrors. Right? So the heat that comes down on here hits these mirrors, and that heat is reflected to some tower that's sitting in the middle. And it's turning some turbine, right? We get some superheated steam out of that. it spins this turbine, and then that provides a bunch of electricity. But here, right, so these are the towers that are just kind of sitting in the middle over here, and all these mirrors here are just reflecting the sun's heat in order to heat up this turbine over here. The textbook put in this, but it looks like there's 170,000 mirrors there, concentrating their light to hit those towers there in order to produce that steam and produce electricity. All right. I think we're going to do one more thing before we move on here. I'm going to change one of these values here. Let's still use the specific heat of iron. But let's put what is the there we go. How about what is the final temperature if we use 60,000 joules to heat up 502 grams of iron and the initial temperature is 25 degrees Celsius. Well, we're still going to use this as specific heat, so let's keep that. This is going to be our specific heat. Specific heat is equal to this value. And we're going to need Q is equal to Q is equal to specific heat times mass times our change in temperature. Well, I think we're going to need to rewrite this real quick. We're going to say Q is equal to specific heat times mass times temperature final minus temperature initial. This is what we're trying to find. Right? We're trying to find the final temperature. So we're going to have to rearrange this. We're going to have to do some work on this. It's just some algebra before we can get started with the actual problem. So I'm going to get these two here. I'm going to probably try and work on this down here a little bit. So here we're going to say Q divided by the specific heat right? So if I divide these by this, I have to do the same thing over here, correct? So this is how we end up with temperature final minus temperature initial. And then we're going to do one more step here. I have to get this to the other side. So we're going to add initial temperature, and we're going to also add initial temperature. So initial temperature plus equals the final temperature. So let's go ahead and solve this. So our initial temperature is 25 degrees Celsius. So 25 degrees Celsius plus the amount of heat we're using. We're using 60,000 joules over the specific heat, 0.449 joules per gram degree Celsius. And the mass of this is still 502 grams. So what is this final temperature? So you're going to solve this, and then you're going to add 25 degrees to it. And what does that final temperature come out to be? What was that? 264 degrees. So final temperature, 264 degrees Celsius. Sounds pretty reasonable. Add a little more heat. This is going to be a little hotter than 250. Right? But here, so we can solve other values here. Right? We can solve for mass. We could solve the specific heat if we had everything else. Right? But there are going to be times where you're going to need to rearrange that formula in order to calculate whatever it is that we need to. So calorimetry, explain the technique of calorimetry, and we're going to calculate some properties using calorimetry. All right, so calorimetry is used to measure amount of heat transferred from one substance to another, right? So calorimetry is used to measure the amount of heat transferred to or from some other substance, right? Heat exchanges. We use some calorimeter. We weren't able to use the calorimeter this semester, but I do have some examples of calorimeters. But in order to understand calorimeters, there's two things that we need to know: the system and what we call the surroundings. So, a calorimeter. We could use this for a calorimeter, right? Anything in here, inside my cup of coffee, is what we consider the system. And anything outside of that is what's considered the surroundings. So we could go as far to say is that this is the surroundings out here, but if we put this on a larger scale, right, is that let's say we do an experiment out in the open here, is that this room would then be the system, and then everything outside of the room would be the surroundings, right? We could do something in the hall. I can open these doors up, and we could do some experiment, and everything inside the building is now the system, and everything outside the building would be our surroundings, okay? So the surroundings is all of the matter, measurement apparatus, whatever it is to determine whatever those values are. So there is a difference between the system and our surroundings. So calorimeters, I'm going to go to this program here. So in the calorimeter, right, in the calorimeter, the reaction itself is the system. Okay. So if I, let's go exothermic. In an exothermic reaction, if we're doing this in a calorimeter, is that this would be my system, and then whatever container I have, the reaction itself is the system, and everything outside of that, inside the container, this is the surroundings. So this is what this is saying here. So whatever the reaction is for endothermic, whatever that reaction is the system, and everything outside of the reaction is going to be our surroundings. And normally it's just, could be as simple as just water. Right? If I do this reaction in water or some aqueous solution, right, that solution is the surroundings, but the actual reaction itself is going to be considered the system. So here we can see exothermic reactions, is that exothermic reactions, they release heat. That's why you see this Q here. We know Q to be heat. There's a release of heat, and that raises our temperature. Endothermic reactions absorb heat. So this is why we see Q going into the reaction. Here's my reaction, but if we have to put heat into the reaction, if I change this to endothermic, and endothermics require some amount of heat, right? This is why we have Q going into that system. And then we can see the temperature just drop right over here. Right? So this is our idea of calorimetry. Right? So, I think we have these is what we were supposed to use. We were supposed to use right here. So here's our reaction mixture, and either this reaction is either going to release heat or it's going to absorb some heat, and that will affect the temperature going increasing or decreasing. So consider a hot piece of metal and some cool water. If the metal is placed the water in the calorimeter, heat will transfer from the metal to the water. We've already talked about that, right? If I have some substance that's hot and I have another substance that's cold, once we put these together, we have some heat flow where heat goes from hot to cold, and then they end up in some sort of thermal equilibrium. Right? So the temperature of the metal will decrease, temperature of the water increases, and eventually we reach some thermal equilibrium. And here's what I had mentioned prior, right? So Q of the metal is equal to negative Q of the water. Well, those sums have to add up to 0, right? This is why they're opposite in magnitude. The example I gave before is that we had Q of some metal that lost 2,000 joules, but our Q of the water gained 2,000 joules. Well, if I add both of these up together, if we take Q of the water plus Q of the metal, is that those will equal 0, right? They're just an opposite magnitude here. So we did just learn some equation here. I'm going to put that back up on the board. We'll say Q of the metal is equal to negative Q of the water. And that's fine. The negative sign is okay there. We also know that Q is equal to specific heat times mass times temperature change. So this Q is equal to this formula, and this Q is also equal to that formula. So we could say the specific heat of the metal times the mass of the metal times the temperature change of the metal is equal to the negative specific heat of the metal times, water here, times the mass of the water times the temperature change of the water. So this, right, because Q is equal to this and this Q is equal to this, is that we can put them equal to each other. And this provides us a really some detailed information that we can solve. So a 360 gram piece of rebar, steel rods used for reinforcing concrete, dropped into 425 mils of water at 24 degrees Celsius. The final temperature of the water was measured to be 42.7 degrees. Calculate the initial temperature of the rebar. So we need the initial temperature of the rebar. So this is temperature final minus temperature initial. So this, right, this is what we're looking for. We're looking for the final temperature here. Specific heat of the metal is the same as iron. Okay, we know that to be, I think it was 0.449, but I'll double check. All the heat that occurs between there's no heat exchange within the outside environment. All right, wow. So specific heat of the metal. So let's set this up here. The specific heat of the metal, I believe, is 0.449 joules per gram degree Celsius. And let me just double check that value here. Iron, 0.449, yes. So it is 0.449. times the mass of it, which is 360 grams, times the final temperature, and we have the initial temperature calculate the initial temperature. I'm so sorry. We're calculating the initial temperature. We're calculating initial. The final temperature, 42.7. So 42.7 degrees Celsius is equal to the negative heat capacity of water, which I mentioned before, and it is on that table, 4.184 joules per gram degree Celsius. Do we have the mass of the water? 425 milliliters. So here's something that we need to know. 425 milliliters. The density of water, if the density of water is 1.0 gram per milliliter, then it's easy to assume that it's just going to be 425 grams, right? So the mass of water says 425 mils. We're just going to put 425 grams. And we know the temperature change here, the initial was 24, the final was 42. So I'm going to erase this right here because we do need to use the board. So our final is 42.7 minus 24.0 degrees Celsius. All right, so let's solve this first. What is the answer over here? And I'm going to adjust this one right here. I need to make a small adjustment over here. Times 42.7 minus temperature initial. There we go. This is what we're solving for. But let's go ahead and solve this first.
Negative 32007.
I'm sorry, negative
32007.6.
And this is going to be in joules. Right. Well, because of this over here, we can't solve this just yet. But what we can do, we can solve this. So what is this here?
Uh, 161.64 joules per Celsius.
All right. So now that I take this, we could divide it by this. We could divide the entire side by both sides. So let's do that. We're going to divide this by 161.64 joules degrees Celsius. And those joules will cancel out, so I will have some negative temperature there. Wish there was a cleaner way to write this. Actually, I think there is a clean. We're still working on the calculation. I'm just going to write this a little bit cleaner. Yeah, I think that's a cleaner way to write it. And what is our answer here?
Negative 198.02.
So now we're at we're at 42.7 minus temperature initial is equal to negative 198.02. So we're going to subtract this from both sides, 42.7 minus 42.7. So negative temperature initial is equal to what? Negative
240.72.
And we know that negative cancels out negative, so our initial temperature is a positive 240.72 degrees Celsius. Let me see, what else do we have here?
Do you recommend us solving for the variable that we need before we plug in the numbers? Or should we do it?
It's up to you. However, yeah, you're going to get the answer the same way. Is that,
Just keep track.
yeah, just if you can keep track of everything, you know, yeah. But, you know, if you're more comfortable rearranging everything first, absolutely do so. All right. What is the approximate amount of heat here? We're still going to use this equation here, but here we're talking about some calorimeter that is not in a container. It has access to atmospheric pressure, but here we have some. This is for a solution, right? So this previous problem here added some metal to some water, right? But we're a little different here because this is some solution into another solution. All right, we're putting aqueous hydrochloric acid and aqueous sodium hydroxide. Both are at 22, and then they reach this temperature change here. So for this reaction here, because they're aqueous, we're going to assume the specific heat of water. 4.184 joules per gram degree Celsius. And what did we say that we could do with the milliliters when we saw them here? We can simply change them to grams. So if we're talking about 50 mils of hydrochloric acid and 50 mils of sodium hydroxide, what is our mass? 50 mils of hydrochloric acid, 50 mils of sodium hydroxide, 100. So here the mass of this reaction is 100 grams. So we could do this. We can say that Q is equal to, the Q of this here is equal to specific heat. We're going to use water, 100 grams, and then our temperature change started at 22 and it ends at 28.9. So 28.9 degrees Celsius minus 22 degrees Celsius. Excuse me. So not as complex as the other one, right? Not as complex as the other one. We're just simply going to use our formula for heat here. So how much heat is produced in this reaction?
2,886.
What was that? I'm sorry?
2,886.96.
So 288.6 degrees, right? And we could do the same thing here because they're aqueous in nature, that most of that's water. And again, we could set this up the same way. 100 mils, 100 mils, so what is our mass? 200. So because they're aqueous solutions, we can still use 4.184 joules per gram degrees Celsius. But this time times 200 grams, and then our temperature change increases to 23.5. 23.5 minus 21.9, I believe that was. Yep. So how much heat is produced in this reaction? One thousand three hundred.
38. No, 1,338.
Like this?
Hmm?
Yeah. So when we have aqueous solutions like that, it's simply a lot easier to calculate. I've seen if we have time for this one here. Burning the bomb chemical temperature increases, the bomb has a heat capacity, submerged in 925 milliliters. How much heat is produced in the combustion of this here? All right. We're talking about bomb calorimeters. Again, we can still use this. But the mass here is going to be different. Right? For this one, if we go back and look at the previous example here, 100 grams and 100 grams, right? Here, we're talking about 0.963 grams versus 925 grams, right? So even though that the benzene, could be solid, could be liquid, but because it's so tiny, it's negligible. We don't have to consider that, okay? So we could just calculate this with the 925 grams. We do have the temperature change. Said it increased by this. We also have our heat capacity. So here we would say that for our bomb calorimeter, this is going to be 784. Wow, 784 joules per gram degree Celsius times 925 grams, and our temperature change is 8.39 grams degrees Celsius. So how much heat is produced in that bomb calorimeter? And this is a bomb calorimeter. So with a bomb calorimeter, the volume is kept constant here, right? It's much different than these here. So here, if we compare it to something like this, as this reaction builds up here, the temperature increases, right? But the volume here, because the atmospheric pressure can change, right? Even though this is building up pressure because the heat's increasing, it's not contained in here. This is an open system because we have some release of pressure here. But with bomb calorimeters, these things are sealed here. Is that here, even though the pressure increases here, there's nothing that changes the volume here, right? Because it's completely sealed. We call it a bomb calorimeter, right? Open it up, right? Bomb calorimeter. All right. Anyways, we won't do that. But again, what was our heat for this one here?
6084428 joules.
Joules. Wow, that's a lot of joules. All right. So the only time that we're gonna need to go to some extents was when we're talking about, I have this large piece of metal right, and we have some water, is when we need to actually use right? When we have to actually use this here, right? So we're talking about some piece of metal and some water. If we're talking about aqueous solutions, we just need to use this, right? Bomb calorimeter, we just need to use this over here. Sorry, the same thing, right? It's when we're talking about some metal and some water in some calorimeter that we're going to need to use those equations over there. So I think that finishes up here. We're not going to talk about enthalpy. We'll talk about enthalpy on Wednesday. Tomorrow we have our lab. This is the lab I wait all year for. We're not going to get very wet, but there is